that A is the matrix 0, 1 half, 1 half, 0. Okay. Well, if we take A times the vector, let's just say 1, 1, well, that's equal to 0, 1 half, 1 half, 0 times 1, 1. That's what this is. Well, that's equal to 0 times 1 plus 1 half times that is equal to 1 half. And then 1 half times 1 plus 0 times 1, 1 half. Well, that's equal to 1 half times 1, 1. Notice what I've done here. A times the vector 1, 1 is equal to 1 half times 1, 1. My eigenvalue, lambda, equals 1 half, because that's all A did. Just simply by virtue of this multiplication, all I did was shrink it by a half. Lambda equals 1 half, and the vector 1, 1 happens to be one of the eigenvectors. Is an eigenvector, not the only eigenvector. Oftentimes, for a given eigenvalue, you have an infinite number of eigenvectors, and we'll show you why in a minute. So again, AX does nothing but expand or contract a vector. Okay. Now, a given lambda can have many eigenvectors. Often we're only interested in one. We don't necessarily need to list them all, so one will do. So a given lambda can have many eigenvectors associated with it, and here's why. Well, if I take A times some number r times x, if I just take any vector x and I multiply it by any number, that's an infinite number of vectors that I can get, and then if I multiply that by A, well, we can reverse this. We can do r times A times x is equal to r times lambda x, because A of x is equal to lambda x, right? Lambda is an eigenvalue. Well, that's equal to lambda times r of x. So notice what I've got. A times r of x equals lambda times r of x. So if I have a given vector x, any scalar multiple of x is also an eigenvector associated with that eigenvalue. Okay. Let's do